And it gives me great pleasure that Professor Bane Vasic is joining us for part 2 of his talk on LDPC codes for quantum computing and quantum communication. And before we begin the talk, I do have some announcements to make about the Communication Systems Laboratory. So I want to congratulate our 4 teams that all had papers accepted at ICC 2022. So I'll just mention the first authors, Beryl Swee, Jonathan Nguyen, Jacob King, and Linfeng Wang, and the large team of co-authors that helped with those papers, many of whom were undergraduates. And in a sense, this is kind of like a testament to the value of the undergraduate research that we did over the summer. There were a lot of great work there. And then we also had really exciting news this week that both of my senior PhD students, Linfeng Wang and Linfeng Wang and Hongjae Yang, both had their sort of flagship journal papers accepted. So Linfeng's paper on RCQ LDPC decoding that has this funky idea of quantizing the messages, transmit inside in the message passing, and then unquantizing them at the nodes so that you don't have to do a table lookup, you just do simple computations. And then Hongjae's paper on list decoding, which we have long been working, we're sort of setting a record for the number of conference papers before we publish a journal paper with the list decoding work. So we had many conference papers. Finally, now we have the journal paper on list decoding and how it provides excellent near random coding bound or even sometimes slightly above the random coding achievability bound for very short block lengths. So I'm really proud of everybody on our team for the great news that we had in the last couple of weeks. So
sounds excellent. Congratulations, guys. May I apply for your group? I do accept some application for next semester.
Actually, you're welcome anytime for our, once you come to the seminars are always open. And in fact, the whole point of having you speak is for us to find ways for us to work together and bring the work that we're doing to bear on the things that you're interested in, the quantum coding and quantum communication. So
yeah, I want a job as a graduate student, no committees, no anything else. Just research.
Yes, exactly. I have to say, I do some work in administration, and the funnest part of my day is when I get to talk with Linfeng and Hongjae and my undergraduates and Amal about the work that the exciting work that they're doing, which is much more fun than figuring out what we're going to do about this student who's upset because they have to take classes in person, and this student who's upset because they can't take classes, they can't take classes in person. So anyway, we're being recorded too. So that was not very, okay. We will move on. I'm going to go ahead and make sure that screen sharing is turned on for Bane.
And I will start sharing the screen.
And we'll turn it over. And so again, typically we hope that people who are able can turn on their cameras so that Bane has the pleasure of seeing our smiling faces as he presents his talk. So with that, I'll turn it over to you, Bane.
Thank you. So like in all series, maybe we refresh our memory about what we talked about in the previous episode. So we basically established that quantum decoding of quantum error low density parity check codes is a problem of syndrome decoding of a code that has some special properties. That it is also a coset decoder, and these special properties of the code have to do with some commuting operators that we haven't described. We also show that there are problems in decoding of these codes because of a couple of reasons, that these special properties, this special structure of parity check matrices introduces special structure in the Tanner code and leads to a cycle, so to a lot of cycles, short cycles, 4 cycles. And we said that lately there were some constructions, several constructions that that start with classical LDPC codes and create these quantum codes without cycles. So I have not made slides about this construction, so maybe we will talk in part 3 or some other time about these new constructions and what kind of interesting properties they have. But today I want to explain reasons for the structure of quantum code. So this would be more, I don't know, less original discussion. So this will be kind of tutorial explaining quantum origins of these properties. So, so there is nothing original in this talk. Only errors are original, and even a joke that this is not original is not original. So it is doubly not original. So let's start with definition of a quantum state. So we use this Dirac notation. I hope you can see my. Do you see the mouse or not? So we have this.
You can see your cursor just fine. Yeah.
In our so the quantum state or qubit is unlike classical bit where it can be 0 or 1, it can be in a superposition of 0 or 1. But these 0 and 1 are not numbers; they are not binary. They are these orthogonal, orthonormal vectors of length 1. And these numbers A and B are complex numbers, and so they make length of this vector vector psi to be 1. So what is important that we, in any of our discussion, we won't be able, or we won't touch these numbers A and B. The nature doesn't allow us to learn them. And when we want to protect the state, it has to be protected without the knowledge of A and B. So
I'd like to take it really slow on this. Can we just go back to that slide for just a second? Yeah. So are you saying that this notation, I don't know this stuff. So, and I imagine that some of our students don't either. And I feel like this is the most, if we don't know this, everything else won't make any sense. So are you saying that this top line where you say psi equals A pipe 0 plus B pipe 1, that I really, what I'm imagining is that 0 actually means a length 1 vector in a direction, and 1 is a length 1 vector in an orthogonal direction.
Exactly.
And that what I really have is an overall vector that then I multiply those two orthogonal vectors by complex numbers whose sum of squares is equal to 1. And that, so I've got a vector that's actually in sort of 2 complex dimensions.
Yeah, so you can actually think of this. This is called a block sphere. So you can imagine a surface of this sphere, and the sphere, it has
4 dimensions.
1, and so this psi is a point on this sphere. So so it is somewhere on the sphere. A and B determines angles. And the thing is, because of noise, this vector can kind of, when you applied unitary transformation that are acting on a closed quantum system, they move this point on these block spheres around.
Okay, so it's a 4-dimensional sphere though, right? Because 2 complex dimensions.
Yes.
Perfect.
So you see. Yes,
so if I think of,
I mean, you have these 2 dimensions, these two orthogonal vectors that are spanning this space, but the coefficients are complex.
Right.
Yeah, so, but the Bonnet, the magnitude square of A and B is like a probability.
Yes. So we will talk about this. So this probability, I have a slide. So if you want to really measure the state, if you try to measurement of a state is really some projection to some some orthonormal basis, to some eigenvectors. So when you project, you will get a number, and this number is, and you will get this projection with certain probability. So you will never able to learn A and B. You can learn these probabilities. You can observe these probabilities.
Thank you very much. So I'm going to move on to the next slides, thinking about a qubit as a point on a four-dimensional sphere or two complex dimensions.
Exactly. So important point is that whatever we do, however we protect data, we really don't want to know. We cannot learn quantum state. We have to learn something about quantum state, maybe parity, something, but A and B we shouldn't touch.
Thank you.
Okay, so now, this is a so-called Dirac notation, and it is I don't know, in the beginning, once when you get used to it, it is a little bit of a turn off because there, scalar products and all other are expressed in this notation, and it is actually a very convenient notation because this, the manipulation of these cats and bras are really intuitive, but this is what we have. So this is this set of vectors that we label 0 and 1 are so-called computational bases, and we are going mostly to work in this computational basis. And there are of course other bases, and one important one is Hadamard basis, where that is slanted, I don't know, rotated computational basis. So it is important to have this other basis, Hadamard basis, because later on we will learn that there will be different type of errors in a quantum system. Some errors will be related to bit flips, and some will be related to phase flips. So bit flips are, you see, more convenient to deal with in computational basis. And whatever bit flips are in computational basis, these are phase flip in Hadamard basis. So you correct flip errors in computational basis and phase flips in Hadamard basis, but they are related. You can express one in terms of another. Okay, so now let's move and talk about n-qubit state. So, in classical, we will just repeat the bit. Let's say in a repetition code, I will take 0 and I repeat it 3 times. But in quantum, I cannot really repeat in this way. There is, you cannot copy a bit in quantum. So the way that we repeat is we kind of expand the space by Kronecker product. So this is what we do. So we imagine that now in n-qubit space, we maybe we look at this vector here, what we have. So we take vector, these vectors x1, x2 to xn. These are all zeros and ones, and we create a Kronecker product of this. So what actually we do is we represent a state psi as a linear superposition, linear combination of these vectors, and these vectors, they are Kronecker, obtained by Kronecker products. So each of them is of dimension of length 2 to the n. So what it basically means that this vector here is really vector that has all zeros except at the position of an index whose binary representation is given by this vector x1 to xn. So you see, it is a very kind of big vector, and you can ask, so is there more compact representation of this? But remember, we also want to have a superposition of states, so we have to kind of have this possibility that we have different ones in this big vector, and then combine them with this coefficient. So you see, this goes over all possible vectors, and these coefficients, these complex coefficients, are again summed to 1.
Is this like in machine learning, they call this one-hot encoding?
I don't know. I don't know what it is in machine learning, but
Okay.
So the point here is that you see, this is a very complicated vector, but there is no protection of any kind. So again, I can think of this as I don't know, some Kronecker product of these spheres, and it lives in some complicated space. But in order to introduce protection, what we are going to do is we are not going to allow. So you see, this is a superposition of these vectors that have ones in different positions among these coordinates. So we are going to just choose some small set of these vectors, and this is going to be a set of vectors that will span our code space. So that will be idea of quantum error correction. Like, similarly what we do in classical. I mean, we don't have all all vectors. We have some set of vectors that represent a code.
Okay, hi, Professor.
Yes.
I'm trying to connect the definition of n qubit with the first page, the 2 qubit, right? I mean, in the first page, in the first page, it is the qubit state is defined as it has 2 dimensions, right? It is 1, 0 and 0, 1. Mm-hmm. But in the n qubit,
So let's suppose, I think I maybe even have a slide, but let's suppose you take a Kronecker product of 0 with itself. So Kronecker product of vector 0 with 0. What does it mean? I get a vector that has that is 1, 0, 0, 0.
I see.
So it has 1 at index 0, 0. What do I get if I take a Kronecker product of 0 and 1? I have 0, 0, 1, 0, 0. So it has a component, it has a 1 at a position 0, 1, etc. Right. So, and then I can continue doing this. So you see, when I do this Kronecker product, I'm just shifting this position of 1 exactly when I want it to be.
Yeah.
Okay. Yeah. I think I have an example of this, but it is not the next. Now, another important thing that now we want to discuss is the action of environment or system that we design as a decoder or encoder on these qubits, on these states. So we can think of this also as logic gates that are applied to these qubits. So in classical, we have really small set of logic gates. If I use NAND, it is enough to represent any other Boolean operation. So it is universal, right? So in quantum, there is more of these logic gates that can act on a qubit, and we can actually show, depending on what kind of action we want, but we can consider this poly group on a single qubit, and these are really matrices. So you can also see that that other operators can be obtained by a linear combination of these poly matrices. And think of this also as logic gates, but also think of this as possible errors that can act on our qubits. So of course there is identity. We have to include these multiplicative factors plus minus 1 and plus minus I so that the group becomes closed. But we really won't care about this global phase, because when we do measurements, this won't appear. So these complex numbers are not going to affect whatever we talk later on in error correction. So therefore we just care about the action of this group. So we have identity. Of course, when I apply identity, it leaves the qubit alone. When I apply X matrix or X operator, you see that if I apply X to 0, it will flip it to 1. If I apply X to 1, if it flip it to 0. If I apply X to this more general superposition of 0 and 1, it will actually just flip corresponding vectors. Similarly, Z, you see what Z does. Z doesn't change 0, but changes 1 by introducing this phase error 1. So, and also, for this more general state, you see that the last bit, the last vector gets flipped. And then Y is just a combination or a product of X and Z. So I won't care about Y because I can express it in terms of X of Z, but you see that I have really two types of errors in systems. So if I want to think of a quantum system as a quaternary system, I will have four possible type of errors. So the same, and by the way, by no means these are only gates. So any unitary matrix could be action of a qubit, and then we will come to this little more. I don't know. This is just some properties of this poly group. And what matters to us is whether these operators commute or not commute. So this detecting whether operators commute or not commute will be used as a mechanism to design parity checks. So this is why we need to understand it. So this is a diagram that shows action of this group element on of matrices on group elements. So for example, if I have if I have matrix I, and when I multiply it with X, which is this red line, I will get matrix X. You see, when I multiply X with X, I will get I. So you see that, of course, X times X is I, but so we can similarly see these other properties. So this express it nicely. But one thing that we can also see whether, for example, we can check whether XZ is the same as ZX. And of course, we will see that it is not, that it is actually minus XZ. So this is what matters. So we'll say that operators A and B in poly group, I mean, the two operators can commute or not commute, or it can anti-commute. But for poly elements, for poly matrices, there are only two choices. They either commute or they anti-commute. So, for example, this is the demonstration, really an example showing that X times Z is minus Z times X. So you see, one thing that we can now quickly summarize is that X commutes with itself. Every operator, so there are trivial operators trivial operator that is I, and there are these non-trivial operators that are X and Z, and Y that is kind of derived. So X commutes with X, Z commutes with itself, Y commutes with itself, but none of these commute. So X doesn't commute with Z nor with Y, and similarly with Z and Y. So you see, if I have some error X, and if I somehow multiply this error with Z, or measure this operator Z, we will talk about this later. There will be, I have actually the mechanisms to compute parity check. So, and we will come to this in a few slides. So the similar holds for n qubits. So I can have, let's say, two operators X and Z, and sometimes I so this Kronecker products X of Z, and I can create a new operator that is obtained by taking a Kronecker product of these X and Z's operating on on each qubit. So this X acts on the first qubit, Z acts on the second qubit, etc. So this is again the same poly operator, but just on n qubits. So there is also a simple way to, and let's say we want to see what this action of this operator on, let's say, all 0 qubit. So you see, I can think of this A as an error acting on this qubit, and I want to see what happens. So this first X is going to flip this first 0 and make it 1. Z is not going to act on 0, nor this last Z is going to act on 0. So, and as we said, Y is both X and Y. So Y will act on 0 and flip it, but will also introduce this factor I. Okay. So, but one thing that we can see is that even number of Z's acting on this state, actually, even if I have state 1, I can, of course, do the same analysis here. But even number of Z's acting on 1 doesn't affect the sign. And doesn't affect of the sign in front of the state. And this sign in front of the resulting state will be, as I said, used as a parity. So now, I think it is pretty clear what these operators do. They act individually on qubits, and each changes the qubit according to the rule that we said, and introducing maybe some factor plus or minus or I or minus I in front. But now I can also talk about commuting operators on n qubits. So let's say this is operator AB, and it is obtained this way as X is, let's say, A is XZ and B is, let's say, ZX. So I want to verify whether this operator AB commutes with BA. So I did some computations here, and then you see that actually these two operators commute. So now I also want to derive a very simple rule for us so that we don't have to go into this poly representation that we have some counting method, some binary, hopefully, representation in which we can really see how we detect errors and whether operators commute or not. It's not changing. Sorry, something is going on. Sorry, let's see. And this is the trick that we are going to use. So remember, we are going to make some simplifications in order to be able to operate with parity checks. Remember, we are going to ignore this complex factor in front, this phase. And this is our new representation of poly operators. So we are going to have these binary vectors. And the first position in binary vector will mean X. So binary representation of a polymatrix X is just going to be vector 1, 0. Binary representation of Z will be 0, 1, and binary representation of Y will be 1, 1. So like what we do in Galois field with 4 elements, right? So we have these elements, 0, 1, alpha, and alpha square, and I can represent this by binary vectors. This is all basically what I'm doing with poly operators. So now, so instead of multiplying these operators, these matrices, I can really show that this multiplication is equivalent to addition modulo 2. So I will be just adding these vectors, adding these vectors corresponding to matrices. So for example, I can verify that binary representation of X plus binary representation of X sums up to identity, to 0, 0. And again, this factor here I will ignore. And I can show that this XZ sums up to binary representation of Y. So now, what is now very easy to do is to verify whether it is very easy now with this representation to see whether 2 operators commute or not. So let's say that I have this operator here, and I want to see whether it commutes with this operator here. So what I really do is the following. This acts on the same qubit, this acts on the same qubit, etc. So what I do is I go and see whether these corresponding operators commute or not. And so I will label with this solid line the fact that they commute, and with the dashed line that they don't commute. So obviously X commutes with X, Z commutes with itself, and Y commutes with itself, but X and Z, Z and Y, etc. don't commute. So you see, what I have is that I have three of these operators that don't commute, and this the fact that it is an odd number tells me that the product is really not commuting. So these 2 operators are not commuting. Now, what you see how this can be done on binary vectors. So what I need to do for binary vectors is to look at I need to see whether there are ones. So you see there is one on the first half of the vector, and here the one in the second half of the vector. So if this happens, that there are ones in 2 different parts of the vectors, this is an indication that these 2 operators don't commute. And of course, here you see that they are on the same side. In other words, these and these are there is no pair of vector 1 here on this side, so therefore they commute. And then of course X and Y and Y don't commute. So this is important because now I want to generalize this to establish this as a rule. And I don't know what is happening with my slides. So again here, let's take these operators A and B, and as we said, there are these positions where they don't commute, position 2 and 5. So I will represent now this whole state as binary vector of, so if there are 6 qubits here, I will represent this state, I mean this operator A in binary notation as a vector that has double length. So, and maybe I do this carefully because this is very important. So similarly what we did with 1 qubit, I also want to represent this and I represented single qubit by a binary vector. I want to represent this Kronecker product of matrices also by a binary vector. So this binary vector will have two components. The first part of the vector, left half, will indicate where I have X operators. The second half will indicate whether I have Y components, Z components. So for example, in the binary representation of matrix A, there will be this left half and right half, and right half. So I will put this 1 here, indicating that X acts on the first qubit. And you see there are no X's anywhere here, so there won't be any red ones here. There is Y that acts on the 5th qubit, so I will put 1 here because Y is both X and Z. So I will put 1 here. And also on this right-hand side, where I put presence, indicate presence of operator Z, I will put, of course, these Z's, these 2 Z's, but also this Y. So similarly here on the vector B, on the left-hand side, I put 3 zeros for ones. I put 1 in both sides because of this Y. And on these last 2 qubits, I put 2 ones only on the right part. So this is my binary representation of a Kronecker product of matrices. So now what I can do is I can verify whether these 2 operators commute just by looking into this representation of this binary representation. So what do I have to do? I have to see whether there are ones on this part and ones on this part that are in the same position. And I count number of them. And I also compare whether there are ones in this part and this part here on the common position. And then I count them. So remember, so if you look at position 2 and 5, we see that there are common 1 in one vector that is on the right-hand side and 1 in B that is on the left-hand side. There is this other vector, there are these 2 corresponding ones, and there are 2 of them. So the fact that there are 2 of them means that these 2 operators commute. If it was odd number of one of this kind of matching ones on left-hand side and right-hand side, this would mean that they are not commuting. I hope this is logical and okay.
Sorry, can you repeat the rule one more time? So we're counting the numbers on both sides, like that match.
So this is what I want to I do. So for both vectors A and B, I have left and right hand side. Mm-hmm. So what I do is I take left hand side of A and compare it with the right hand side of B. Mm-hmm. Because why I do this? Because this left hand side corresponds to X, presence of X, and right hand side corresponds to presence of Z. So I want to see how many products of X and Z's I have, mm-hmm. Because they don't commute. So when I compare this, I will find in how many places I will be multiplying X and Z. Mm-hmm. So if this so this I'm sorry.
Nice.
So this is the first thing that I do, and then I also take left-hand side of B and right-hand side of A, and then I also do the same comparison, do the same counting. So I think I have this on the next slide.
Okay.
So I have this, I will call it X component and Z component of A, and B component and and X component and Z component of B. So I do this cross kind of check. So what I do is I compute this number. I multiply AX and B. So these are all now binary operations. And so by doing this, I'm really counting number of these positions where I have ones in both vectors. So this is how I will compute how I will define parity, and this product, this type of product between two vectors A and B, I call symplectic product. So this symplectic product is our tool to verify that two operators commute. If symplectic product is 0, they commute. If it's 1, they anti-commute. Okay, so this is, so to summarize, there is this correspondence, this poly to binary isomorphism. So we have this representation of poly matrices, and then we have multiplication that corresponds to bitwise addition, as we show, and then this commutativity is verified by a symplectic product. And then, of course, there is a GA4 representation, but we won't need it now, so I'll skip this. Okay, so this is one little complication in our lives, because now instead of ordinary scalar product that we are used to, we need to work with this symplectic scalar product. So when we are multiply, when we take a scalar product of two vectors, or errors or code words, we need to do it in this symplectic product. But we can show that this vector space with a symplectic product is also a vector space, right? So that all properties will be valid. We won't need this. Okay, so I think we have now all tools now to define a code. This, and I realize that we have 10 more minutes. And by the way, I have also another meeting later, so we better stop. But at least we have some background so that we defined a quantum code. And then I'll share the slides and we can talk other time. And sorry, I thought it was better to go slowly and explain than try to cover everything. And
no, there's no point in having a very high rate of information transmission where there's no reception. So I think we maximize mutual information.
So this is, I see on this other screen that it is slide 79 of 133 slides. So don't worry. I mean, okay, so here is
Bane, before going to the entanglement in the previous slide, the channel model you said is quantum depolarization channel with certain probability of flip, phase, or bit flips. Can we model that, or is it isomorphic to the two binary channels, binary symmetric channels?
Yes, and this is something that we discussed earlier in the previous talk when we talk about Calder-Van-Shore and Steen codes. Remember, in these codes we protect code space so that we can correct separately X errors and separately Z errors, because they are not correlated. They are not dependent. So indeed, so if our code is designed so that we correct these two type of errors separately, I indeed treat them as two binary symmetric channels. So in the parity check matrix of the code, there will be part that will have, so remember, X stabilizers can catch Z errors because they anti-commute. X stabilizers can catch Z errors because anti-commute. So imagine that that you have a code and they're measuring just X stabilizers. So this will be able to correct all Z errors. I mean, certain number of Z errors and opposite. So this is the idea of CSS codes. And then and this is, by the way, a very powerful class of codes. And for us, it is of great interest because now we have really two parallel binary symmetric channels. We observe a syndrome, and we decode independently. We observe the syndrome from, in these channels, and then we do this syndrome coset decoding. So the operation is totally classical for both channels. Now, if there is an error or correlated error, now there are different approaches. So one approach would be to, I don't know, do some kind of a turbo stuff between these two channels. And I haven't seen this type of work in literature. Although, for us, it is natural to consider. So you know that there is some probability of Y errors, and then you are decoding, trying to match, kind of favoring positions when you have common error. So this is a new, by the way, at least I don't know if anybody worked on this.
No, I'm saying that because interested students with the knowledge on, classical coding and decoding, in particular LDPC codes and LDPC decoders, can start, to design these codes, except that the H matrix has a constraint that you discussed last time. And then, at the receiver, instead of direct observation, you use syndrome, and then you can decode and find performance. And construction most probably will be based on the circulant, except that you have to consider the constraint on the H matrix.
Yes. So this is precisely, I don't know, spirit of this talk and our discussions and collaboration, that there is a lot of classical problems and things that we know how to do that quantum people haven't looked into and are not aware. So I tell you, there is these big classes of codes that are now gaining popularity, so one is so-called hypergraph product code, and the second is what they call lifted product code. So lifted product codes are your protographs. So of course they don't know about protograph codes, but what they do is something similar. So what I want to do for next time, or it doesn't have to be a talk, but when we talk next time, I want to prepare some slides on these code constructions so that we see how Tanner graphs on classical codes translate into quantum codes. So there will be kind of three-part type graphs. There will be, let's say, a code that protects for X errors, code that protects for Z errors. So there will be, two branches, one Tanner graph up, one Tanner graph down, and they cannot be arbitrary, these graphs. They have to have some properties, and we'll talk about these properties. And these properties come basically from the fact that rows of parity check matrix should be orthogonal, right? And this orthogonality is defined with respect to this symplectic product. So this is what defines the structure of this code.
I see. Okay, thank you.
Yeah. Okay, so I suggest we stop here.
Yeah, I think that's a good idea. So obviously this is a journey and we're beginning. So we'll have you come back for another talk. But in the meantime, I think what's needed is, because this feels more like a course than a lecture. And I feel like for the people who are interested, maybe we should have we need a problem set. We need some exercises to make sure that that people are with you up to this point. I wonder if there's already available some like a course online or something where we could get a problem set or something where we could make sure that we're on the same page with you, because you just taught us a sort of about the poly group and about the binary representation of the poly group. And I feel like there might be some simple exercises that either we can do them or we can't. And if we can't do them, that means we're not ready to move on.
No. So I think so it is indeed like a course, and what I promise to do in this center that we have, this Quantum Internet Center, is to develop with my postdoc Narana, and to develop this course, which will be kind of a little bit of classical and quantum. But I like, I'm a classical guy, so I like to see this classically and kind of ignore. There are a lot of physics details in quantum consideration. You know, what is a stabilizer, how you measure it, etc. But there are classical kind of mathematical setting can be made classical. So what there are fortunately some good papers to read. And also good papers on quantum LDPC codes. So one being Mackay's paper. It was a old paper when he introduced sparse graphs, and he talks about some of these constraints that we discussed. So I can look and send you some of these papers. They are fun to read, more fun than this lecture.
No, this has been great. Actually, what I think I'm going to do is, Bonnie, I'm going to open up a channel in our Slack on quantum and invite you to join it. And you could drop in a couple of papers. And then we're going to work out, I think before we have you back, let's figure out which people are interested in going more deeply among the people who are here or just people in the group. And then I think we need to get together and see if we understood what you've said before we bring you back. Because I know I'm not quite ready yet. I would need to do some exercises and confirm some things that you said on the slides before I'd be comfortable going forward. So, and by the way, we are going to have talks next. We don't normally run CSL seminars every week, just to give people a chance to breathe. So we're taking next week off, but then on the 18th and the 25th, we're going to have double headers both days of people giving their practice ICC talks, and which are 15 minutes each. By the way, Bonnie, Mike, you guys are always invited, but of course never required. So come if you want. But we'll be having those 15-minute ICC talks with sort of 15 minutes of feedback and questions for 2 topics each of those 2 weeks, February 18th and 25th. And then probably we'll have you back sometime in early March, Bonnie, to take us on the next step on this journey. And then
that would be good. You know, by the way, this was a good exercise because these are slides that I made really for you. So, and then I'm happy because I think these are general slides. It's like a tutorial. So you kind of push me to do things that I was supposed to do already.
Good. So I'm excited about this journey that we're on. I think we're going to get somewhere. I guess to sort of say back what I think I'm hearing is that quantum communication and computing has a pretty high barrier to entry. You know, we have to figure this stuff out before we can do anything. But if we do the work and overcome that barrier, there is some low-hanging fruit for a code designer who already knows how to design good codes to apply what we already know to these problems. But before we can do that, we have to get over this barrier and understand the jargon and understand the quantum environment in terms that make sense to us.
So all is true, Rick, except one small thing that about these low-hanging fruits. So, so there are fruits and they're sweet, but they're not that low-hanging. But we can climb.
Okay, good. Well, I'm okay. Most of the work that I do, we commit to a problem for years and then can write like the list decoding paper that was just is published today as an example of that. So I don't mind taking the time to get the results. So anyway,
I maybe I told you, but it is when I started this quantum thing. I feel pretty comfortable going to coding conferences, or when I talk about data storage, you don't know a lot, the channel, you're confident, and these are things that you are learning, and there are people who know this better, but who cares? I mean, it is fun, and then we know what we know, and there are things that I think we can contribute, and these things are really, you are measuring these syndromes and you have to decode it. You have to do the decoder throughput must be faster than the rate of generating syndromes. Where are you going to store this? I mean, you are going to put this decoder in refrigerators that is cooling around 0 Kelvin, absolute 0. I mean, it cannot dissipate a lot of heat. There are obviously some power constraints and harder design constraints that we know how to deal with. So that's the plan.
Very exciting. All right. Well, I think with
okay,
that,
thank you very much, everybody. It was really a pleasure to talk with you.
Okay, thank you. I really appreciate your time. And I'm now so thank you very much, Bane. We look forward to having you back. And now I'm going to stop the recording.
Thank you.